Alright, so what we're looking at here is on page 73 in our notes. This is still day 30, and we're looking at simulations. So we've got a member of the Phoenix Suns. He's considered a streaky player, meaning that he has times where he makes a bunch of shots and times where he just doesn't make anything. So many people believe that his shots are not independent. If he makes a shot, they believe he is more likely to make his next shot and vice versa. As evidence, people point to a recent game where this player took 30 shots and had a streak of 7 made shots in a row. Is this evidence of streakiness, or could it have occurred simply by chance? Assuming that this player makes 60% of his shots and that his shots are independent, design and conduct a simulation to estimate the probability of having at least one streak of 7 or more shots, made shots in 30 attempts. So we're looking for, when we do our conclusion, the probability that he has a streak of 7 or more made shots by chance alone. So we're repeating, this is the component to be repeated. And we are looking at making shots. So the way we're going to model that is with our calculator using random integers, and we are going to let the numbers 1 through 6 be shots that he's made, and 7 through 10 be shots that he's missed. 60%, so if you use the numbers 1 through 10, then 6 of them are 60%. So 60% of the time, let 1 through 6 be shots made, 7 through 10 be shots missed. So the trial, we will select 30 random numbers from 1 to 10 to represent the 30 shots he takes. Alright, so what's our response variable? Is we will count the longest streak of shots made. So in other words, we're going to count any streak involving the numbers 1 through 6. As soon as there's a number like 7, 8, 9, or 10 thrown in there, then it's just not gonna, we just stop counting. So here's an example. If I go to math, turn my calculator on, go over to math, hit math, over to PRB, and I hit 5, random integer, math, PRB 5, and I want numbers 1, comma 30, sorry, not that, 1, comma 10, comma 30. Again, random integer, 1, comma 10, the numbers from 1 to 10, and we want 30 of them. And then if I hit enter, what I have here, I'll just write mine down, 7, 4, 10, 3, 4, 8, 10, 1, 5, 9, 6, 7, 1, 2, 1, 9, 10, 5, 4, 4, 9, 4, 3, 5, 4, 9, 3, 3, 2, and 7. Okay, so there's all 30 of mine. So I hit math, over arrow twice to PRB, 5 down to 5, and hit enter, or just hit the number 5. And so I had random integer 1, comma 10, comma 30 of them. So now I need to go in order, and I need to count. So like here's the first shot that he made, but he didn't make one right after it. So 3 and 4, there's 2 in a row. So that's our biggest streak so far. So then, well, there's 1, 5. There's another streak of 2. It's no bigger than that, so I'm not going to worry about it. There's a streak of 1. Okay, here's 1, 2, 3 shots made. So that's going to trump that first one. So there's a streak of 3 shots made. Here's another streak of 3, but we still just have 3 as the highest. Here's a streak of 1, 2, 3, 4. He made 4 shots there. He also made 4 shots here. So in my example, he had a streak of 4 shots. So again, that's our response variable. We will count the longest streak of shots made, 1 through 6. So we had a streak of 4 shots. All right. So now I've also done 10 other trials. So in my 10 other trials, trial 1, I had a streak of 7. So this is the streak of how many shots he has made. Actually in trial 3 he made 14 shots in a row. And then 4 and 3 and 5 and 2. So what I'm going to do is I'm going to graph the results. And so if I make a graph of my results, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, because I do need a 14. So the title on the bottom is the longest streak. And I had 10 trials, so my probability is going to be out of 10 trials. So the results in the first trial, he had a streak of 7, and then a streak of 5, and a streak of 14, and a streak of 4 and 3, and another streak of 5 and 2, and 7, 5 and 5. So there's a graph of my results. So the probability, so in my results, he had a streak of 14. That was the longest streak. Not very consistent, and most of his streaks were 2 to 5. Okay, so what's my conclusion? The probability that he has a streak of 7 or more. So remember, we were looking for the probability that he has a streak of 7 or more. So probability that he has a streak of 7 or more by chance is approximately, okay, how many of our trials had 7 or more? 1, 2, 3 of our trials had 7 or more, is approximately 3 out of 10. So the probability they had a streak of 7 or more by chance is approximately 3 out of 10. It happened. Okay, it happened 30% of the time. Okay, so it is possible. So in other words, the conclusion here would be he is not a streaky player. We don't have convincing evidence that he's, instead of saying not, we do not have convincing evidence. Okay, because by chance alone, somebody who doesn't know anything about basketball made 7 shots in a row, 7 or more shots in a row 30% of the time. Alright, so now we're on page 74 in the notes, and we're going to start getting some notes about probability. This is in chapter 14. The probability of an event is its long-run relative frequency. For any random phenomena, each attempt or trial generates an outcome. An outcome is what happened on the trial. For example, each time we waited for a bus was a trial. We didn't actually wait for a bus. We've awarded parking spots to seniors, and we've seen if people have ESP, and we've also seen if someone was a streaky shooter. So instead of individual outcomes, we sometimes consider events, which are combinations of outcomes. For example, a trial consisting of rolling a die, the outcomes would be 1, 2, 3, 4, 5, 6. An event might be rolling an odd number, or not rolling a 2. So those are examples of events. So on a die, you're going to roll the die, that's the trial. Our outcomes would be 1, 2, 3, 4, 5, 6, not rolling a 2. So rolling an odd number, the probability of rolling an odd number, that's how we write probability problems. We write P, and then in parentheses, rolling an odd number, and you read that probability of rolling an odd number. So there are 6 total outcomes in the die, and how many of those are odd. That's what goes on top, and there are 3 of them, those that are odd. So 1/2 of the time, it's a 50% chance that you'll roll an odd number, not rolling a 2. The probability of not rolling a 2 is what out of 6? Well, how many things are not 2s? There's 5, so 5 out of 6. If you want to know about combinations of outcomes, it helps if the individual trials are independent. For example, when you're dealing with the die, you can roll a die and get a 2, and the next time your chances are equally likely of getting a 2. If trials are independent, then the outcome of one trial doesn't influence or change the likelihood of another trial. For example, when we were waiting, I don't really want to use waiting for the bus, so let's just say when we were selecting people for Stugo, okay, well, that's not a good example. The streaky shooter one is a better example. So if trials are independent, then the outcome of one trial doesn't influence or change the likelihood of another trial. For example, when we were back in this problem here, we were opening cereal boxes and pulling toys out. This would be a good example. Every time I opened a cereal box and pulled a toy out, the next cereal box was totally independent. It didn't matter what I got in that first cereal box. So, however, if we are drawing cards without replacement from a deck, the trials are not independent. That would be like the Stugo example, okay, where we were drawing numbers out and we didn't put them back. So the same person couldn't get 2 parking spots. So it's not independent in some cases. If we draw a club on our first trial, if we're dealing with a deck of cards, then we know the next card is less likely to be a club because we've already pulled the club out. So there's fewer clubs than all the other cards. So this is why casinos use 6 decks for blackjack instead of 1, because people can count and see what happens. The law of large numbers, this is a really important law, says that the long-run relative frequency of repeated independent events gets closer and closer to the true relative frequency or probability as the number of trials increases. So just as an example, if I flip a coin, and I flip a coin 5 times, okay, and I happen to get 5 heads, it looked like maybe this coin was geared towards heads. So you might think that, hey, I'm going to bet for tails next time because I'm due for tails. Well, that's not really the case. Please don't get into any thoughts about that. You're not due for tails. When you have, this is a small number of trials if you've only done 5. And so you might get the misrepresentation that, you know, after a certain number of trials, you have a lopsided number of heads. But if you actually flip that coin, say 1,000 times or 100 times, what happens is it'll probably even out, and you might end up with like 48 heads and 52 tails. So that's kind of the law of large numbers. The more you do something, the closer it's going to get to the actual probability, because the true probability of getting heads on a flip of a coin is 50%. So if you just do a few number of trials, it might not represent the 50%. You might not have, out of 4, you might have gotten 3 heads. So it might look like it's a lopsided coin. That is not the case. The more trials you do, the more it's going to actually even out. So like rolling a die, if you roll a die, you know, 1/6 of the time you should get a 1. So the picture below shows a relative frequency of heads after 100 flips of the coin. Notice how when there are a small number of flips, the relative frequency of heads can vary quite a bit. Okay, and it gets closer to a half the more trials you do. Many people misunderstand the law and apply it to situations with a small number of trials. However, since the trials are independent, the probability that the coin lands on heads never changes. The last blank is large number of trials. You can read the rest.